Okay, so I'm going to get started. Today we're going to talk about ordinary differential equations. This is in the last appendix, I think appendix C of the textbook, and a lot of it has been used in our project 3. We haven't given a lot of background, but I think there's enough background for you to get going. But if you are having trouble understanding that background of ordinary differential equations that we've used in our project, in deriving models for Descartes, then this should be helpful. I'm going to write from scratch 1 or 2 functions that we've given to you in the project that should hopefully help you understand them better. So let's talk about what ordinary differential equations are. So ODEs are just equations with a derivative term in it. In robotics and then especially in controls, we end up using a lot of these equations to represent the dynamics of our systems of interest because we want to see how the world evolves with time. So we have these equations that basically help us operate in a 4D world, where the 4th dimension being the time dimension. And they just help us see the dynamics of the world and plan or set our controls accordingly, which is what we've done in our projects. So let's talk about the cart example, which is a point mass cart example. And let's see if we can derive it in the form of a differential equation. So let's see here. So a differential equation is anything of the form of x x dot equals ax plus bu, where x is your state and u is your control input. Basically, the force or disturbance that you're applying to the system intentionally goes as your control input, usually recognized as u. This is standard notation. So let's see, for our cart example, what we basically have is we have a cart that we're moving with a force F in the forward direction. Your state is basically the distance x from the origin, and also the velocity. So here, let's call it P and V. So your position and your velocity with respect to the origin is your state vector. And we're also going to use Newton's second equation of motion which is the famous F equals ma. So using that, I want to write down my state, my x is x and v. So my x dot is basically v and this acceleration. Can I write this down in terms of, and u is then my force. So then my ODE can be written down as x dot equals 0, 1. The first equation will simply be this. 0 times f. And then the second equation is basically acceleration equals a is equals f by m. So this will be 1 by m and 0, 0. So from here we get two equations. And the next step is, because it's a differential equation, the way that we've learned to solve things is linearization. So we do linearization of, I write down the two equations separately, which is x dot, which is the same as dx of t with dt equals v of t, and wait, this is confusing because I started using p instead of x, and then halfway in there I changed it. So p, and this is p, and then this is p dot. This is basically p dot, which is dp by dt, and then your v dot is dv by dt, which is the acceleration, which in this case equals f by m. Now we're going to use symmetric, using a forward approximation. So using forward difference, I'm going to write these equations down. So using forward difference, we will rewrite 1 and 2. And by that logic, our equations become, I hate it when it does that. Our equations become p plus t plus delta t minus p of t, instead of p, let's use the step size h because we're used to it, by h. This is dp by dt is equal to v, which means p of t plus h equals p of t plus h times p of t. And then we're gonna use the concept of discretizing time. So we discretize time as, which is our standard way of discretizing. We take the kth interval of time to be k times h, and by that logic, p of t plus h is basically just pk. Similarly, v of k plus 1, or I think the easier way is just, we'll just replace that in there. So by that, our equation just becomes simply pk plus 1 equals pk plus, instead of h, we can use delta t. Or h, it's the same thing. I'm going to write this tk is k times delta t. This is equation 3 that we got from equation 1. And now let's do the same thing to equation 1. Then for equation 2, we do the same thing. We have v of t plus delta t minus v of t by delta t equals f of t by m. And discretizing, we get v of k plus 1 equals v of k plus f of t by m times delta t. So this gives us a linearized model. So we can write the final linearized prediction model can be written as our state x, our full state x. So x k plus 1, which is p of k plus 1 and v of k plus 1 equals a x k, which is pk, and vk plus b times uk, which is f at the kth time. I should have discretized f as well. So f, k, yeah. So from this third equation, we got pk plus 1 is p of k plus delta t, I forgot v of k here, v of k, delta t times v of k plus 0 times fk, and this becomes, from here we get vk plus 1 is vk. Now, this is 0, this term is 1, plus delta t by m times fk. And then finally, we're going to call this a, and we're going to call this b. We'll call this u, and we'll call this xk. And our cart model is xk plus 1 equals a xk plus b uk. And that is our final cart model. So let's write down a function that will return this A and B matrix for us in Julia. So I'm going to go here. We're trying to find the cart model. So the first thing we need to describe is dt, which I'm going to take 0.1. Then from our calculation, we had A, which was 1, dt, 0, and 1. And then the B was simply 0 followed by dt, and I'm going to take m to be 1, which is basically saying it's a point mass, so dt by m. I think we ignored the m in our final function in the project, but the idea is this, and then you can just say return A and B. And this should be a function that should be able to give us a model for our cart. Now, how do we find solutions of differential equations given a model like this? Well, we already have a solution in the sense we already solved our differential equation using what we know to be, this is called Euler Integration, first difference method. So the next step should be to, if you're given A and B and an initial position x naught and some control u, are you able to predict your next steps? So in the sim model, nominal, which means no disturbances, it's the ideal world. We haven't accounted for friction. We haven't accounted for air drag or any of that that might cause our model to be imperfect from the world. We're going to consider that the world here is perfect. So what we need is, given an initial point, we want to find out our trajectory x. So I define the first x to be x naught. And I am also given a planning horizon, which is basically the amount of time that I'm supposed to simulate this loop for. So I'm going to take that to be whatever is the length of my control. Basically, that's how much time is of interest to me. Then I want to go from 1 to n, and I find xk to be the kth element of my trajectory, and uk to be the kth element of my control. Now that I have both of them, I'm going to find the next xk, which I think we've called xk plus 1 like that. Simply a times xk plus b times uk, which is a simple application of our control. And then I append that into my existing trajectory, which is an x. And to x, I will add xk plus 1. I keep doing that till whatever is the interest of my time. And then finally, I will return my trajectory x. So we have this function. And now we want to do the problem in our project, which is we want to drive our cart to a position that is 15 meters away from its initial position, which I'm going to take 0, 0. And I want to go there in 20 seconds. So let's go back to the drawing board. Let's go back here. And let's try to find out by hand a sequence of controls that will do that for us. So let's say naive control selection using equations of motion. I think that was the Newton's law, second law of motion. I'm going to use equations of motion, which is different from laws. But equations of motion that we're going to use. So if you studied any physics in high school, what we do is we take a ball and then we try to find if I have to send the ball to a height h, how much height will the ball achieve, given this is the gravity, and what velocity the ball should have in the beginning. Find u such that the ball achieves this much height in this much time, and so on. So we've done problems like this. We're going to use equations of motion to solve for our card problem. So our card problem is simply, we want to go the distance, which in this case I'm going to say s equals 15, and the total time is 20. Our final velocity is 0, and our initial velocity is 0. Our final position is 15, and our initial position is 0. So if you remember, when we throw the ball in the air and we're trying to solve for it, we assume that we're going to find the time of flight for half of that trajectory because we know the velocity at that position. So we're going to kind of apply the same logic here, where I'm going to find out for t equals 10 seconds, I have u equals 0. I have s equals 15 by 2. And what else do I know? Yeah, I think that's all we know. And we're going to apply equations of motion. Let's apply the first one, which is v equals u plus 8t. U is 0, so v is a times 10. Or yeah, I think so. We don't know v, which is the velocity at t equals 10 seconds. We're trying to find that out. And we also don't know the acceleration at that point. So from here, we just get the relation that v is 10 times the acceleration. We're going to keep that as a b. Then another motion of equation that we know about is v square minus u square equals 2a times s. Now, I know v is v and then u is 0 equals 2 times a, which is v by 10, times s, which is 15 by 2. I cancel this out, and I cancel v, assuming v is in 0, because that would just be, because we want to keep moving, so v should actually be maximum at this point. So v is in 0. We find v to be equal to 1.5. So from there, I'm trying to find the force. So what we're trying to find we're trying to find U, which is the force, which in our case equals MA, and because M is 1, it equals A. But in point mass world. So if V is that, then A is basically V by 10, which is 0.15. So we should apply, so our control sequence, U with respect to time, is basically we're going to apply 0.15 for t less than 10 seconds, and then minus 0.15 for t, one of these is greater than 10 seconds, to 20 seconds. We found out this part of the problem. The second part is very similar and intuitive. If you've done any of the problems like the ball throwing in the air, you probably know how that came about. So that is my most naive guess at a control that will get me to a position of 15 meters in 20 seconds with that kind of control. So let's use our simulator. We have a simulator, and I also copied the code for animation from project 3, just so I don't have to write it down again. And I wrote down the manual control. You can see it's 0.15, which we found the value for the acceleration. And for 100 time steps, which is basically 10 seconds, because dt is 0.1. So for 10 seconds, I'm going to give it the acceleration 0.15, and for the other 10 seconds, I'm going to give it minus 0.15 acceleration, and that should, in theory, drive our cart to the required solution. So we set x naught equals 0, 0. So at the beginning, our position is 0. We're starting from the origin, and our velocity is 0. There's standing still. Then I get a trajectory. I simulate my model, open loop. I gave it the A, the B, x naught, and the control, which was U manual. And let's see if our cart actually will go to a position in the world that is 15 meters away in 20 seconds, and it should also stop there. So it does, as we expected, because equations of motion have been there for a long time. Let's see what that looks like, what our control input looks like. So for 10 seconds, we gave it 0.15, and then for the rest of the 10 seconds, we gave it minus 0.15. If we were looking at our solutions, if you've done this portion of the project, if you find out the norm of this, it is going to be, I think, 0.15. As you can guess, this isn't the minimum norm solution. It's actually pretty jerky. So what we're doing is it's kind of like saying, I want to go 15 meters. What I'm going to do is I'm going to put my pedal, give it full gas for 10 seconds, and keep pushing forward. And then as soon as the time is 10 seconds, I'm going to put my car in reverse and try to apply an equal force in the opposite direction. So it's pretty drastic, and it's not going to be an easy car ride. So it's going to be very jerky. Not throughout, but especially at this point, it's going to really be uncomfortable at t is equal to 10 seconds because it's a very big discontinuity. So we don't want to do things like that. Also, we don't want to be giving this high an acceleration. We don't want people to be going that fast because it's uncomfortable. So the way that we're doing this in our project is we're trying to find the minimum norm solution. So the given system, the way we do it is if we're given a time instant, what we can do is we can find our position, or instead of saying position, we should be general enough and say we can find our full state, which is position and velocity, given an initial position and a very good model of the world. So the question is finding state x given x naught and u for a time t. How do we do that? So if we're given x naught, we can get x1 by simply forward propagating using this logic. Now x2 is simply a times x1 plus b times u1. If I open this up, I get a times ax naught plus b u naught plus b u1. This becomes a to the power 2 x naught plus a b u naught plus b u1. And if you keep going, you get the nth solution to be a to the power n x naught plus a to the power n minus 1 bx bu naught plus a to the power n minus 2 bu 1 all the way to bu n minus 1. So just forward propagating our model, given a discrete time instance, we're given a starting position, the control at each of these times, and my world is predictable, so I can keep predicting my state at all of these positions. So if I have a model like this, and I know my terminal state, so I know my x goal, my terminal state is 15, and also I want to come to a stop there, so my velocity is 0. So this is my x goal. And my n is 200, and time is 20, and dt is 0.1, and n is t by dt, so it makes sense. I'm given all of this, and I'm also given these equations, so my final question should be that my xn, which is this, so my a times n, so basically my state at the nth point, xn, is basically, if I write it down, a times n times x naught plus this whole an minus 1 b an minus 2b all the way to a times b, and the control sequence u0, u1, all the way to un minus 1. Now, I'm trying to find out my control sequence. So this is my vector of unknowns. I know my xn, which is the x goal, and I know my x naught, which is the initial position 0, 0. can I find out this vector of unknowns? So what I do is I write down this equation, the xn equation, as xn equals s times x naught plus m times u sequence. I'm going to call this u sequence. This is what we're trying to find. And then this is our S, and then this is our M. So now we see it does indeed make sense. And do we know how to solve for this vector of unknowns? Let's rearrange our terms so we can see this more easily, because we're used to ax equals b, so this might be not intuitive. So basically, we're trying to find m times u sequence equals xn minus sx naught. For our case, this will just be 15, 0 minus, we don't care what s is, this is zeros, right? This is just 15, 0. So we're trying to find m times u sequence 15, 0, and our u is, at each time instant, our control is basically just the acceleration. So u basically is a n cross 1 matrix, and then m depends on a time instant. So if you look at it from here, it is A is a 2 cross 2 matrix and B is a 2 cross 1 matrix. So M is going to be A times B is always 2 cross 1. So if there's n time instance, M is going to be M cross 2 cross M, N. So it is 2 cross N. So what do we note? We note that for our M matrix, there's more, if this is M was M cross N, we saw that in underdetermined, so let's go here. For system of equations, this is a note, this is an aside, so the notation is going to be different. Ax equals b. We have a system of determined system if A was M cross N, if N is greater than M. So the system of equations is underdetermined, and our solution for an underdetermined system of equation, our A star, if X star, if you will, so our X star for an underdetermined system of equations is, if I'm not wrong, A transpose times A transpose times A transpose inverse times B. Now we can use LU decomposition, QR decomposition, and whatever we want to not have this inverse term in here. And I think that's how we've done it in the class notebooks, but for the interest of time here, I'm just going to use the inverse function. It's not the best way to do it. It's definitely not recommended, but we're going to use the inverse function, and we're trying to find out a U sequence that will satisfy this control. So our U control or U sequence is basically going to be M transpose M times M transpose inverse times, it came out to be xn in this case, but in general it will be xn minus sx naught. Let's put that in our Julia code. So I think I ended up doing this minimum normed underdetermined system, and as I said, I used inverse for that problem. And the next thing is we're going to want to find our S. So S equals, so let's run this. Let's have that function in there. Now we need to give it an S and an M. So our S, did I define N? So all of this is defined. Let me just copy it. Yeah. Just so we know we don't lose track of these things. So I have S equals A to the power N, and for K equals 1 to N, I'm going to make M equals my I'm going to have M equals A times M space B, and I'm also going to need to, so I think I'm going to start with M equals just the B, and I'm going to make this 2, and then move it, yeah. A times M slash M. Okay, no, let's do that. Let's make this an empty array of 64. Let it be two-dimensional. I'm going to use undefined, and then 1, 0. It's fine. Make that B. That's your M, and then you're trying to find U control to be the least squared solution. So first let's also define an X goal, which is 15 and the speed is 0. And then your U control is the minimum norm underdetermined solution, where A is M, and then your B is S times X goal minus S times X naught. We need the dot operator because they're both vectors. We need a vector. Or actually, we could just do it without it. So yeah, that should do the job for us. Let's see if it does. Unless I missed something. I did. So in line 7, line 6. So I call it an array of load 64, comma 2. Am I missing? With 10. Got type array. But I want it to be an array. Oh, my brackets are wrong again. Okay, and now it has the right dimensions. So the number of rows should be 2. That number of rows was 2. So it makes sense. Yeah, and that's the control we got. Let's see how it does. And while we're doing that, let's also plot it like that so that we can see we actually did good. So we know the norm of that was that index. Okay. Just gonna use that. What? Attempt to access. Why? Let me run this again. Oh, actually, we didn't even predict. So, got the control input. I'm still plotting the other one. So I should be plotting the control I just plot. So my x trajectory nominal is sim model open loop. I gave it a, b, x naught, and u control. Oh, my bad. Oh. It's fussing about the time. X and Y are not equal in length. There you go. So now our control, the value is a lot smoother than this jerky control. And Let's also display the norm. So show the norm of U control and show the norm of U manual. Let's actually see that it's minimum norm, so that should be less than that, and I forgot to do using linear algebra. So indeed, the norm of our control sequence is a lot less than the norm of what our guess was, so it does indeed give us, well, we can't say minimum from just that, but we know from math that it was actually a minimum non-solution, so that is expected. So that's how we're trying to do controlling our cart in the open loop system, which is the first part of project 3. Then in the open loop, we also have a speed control. So instead of doing like the full speed control, what I did was another example of the same, where we're given a reference, and you're trying to so let's say I wanted my goal to be 15, and I also wanted the speed by then to be 1 meters per second. So I'll do the same thing, and I'll put my x goal to be like that. How would you control the sequence then? It's the same thing. I'll do that, copy my code, and I'll plot it for this specification. It shouldn't be very indicative because we're going to move past 15 because we're still going to have a speed of 1. We're going to get to 15 in 20 seconds, and we're still going to have a speed of 1. So we won't stop there. So it makes sense. But I think what we were given was a tracking problem where we only wanted to look at the speed. So basically, for speed control, we're back out here. We don't care about the first row. So our first equation is useless to us. So we're given n variables and one equation, which is the equation of our velocity. So basically, for speed control, for tracking speed, we end up using the second row of our m. So the second row, which should be a 1 cross n vector, times the u sequence, which is still an n cross 1, equals to our velocity, which is 1. So it is v reference, which is 1, which is also a n cross 1 vector. So let's do that. Let's put so we don't care about the goal anymore. It's just going to be the second row. Because it's a row, we're going to put a transpose. And then here, it's just going to be x goal minus sx naught is always 0. So I'm just going to put x goal of 2, which is basically the term 1. And yeah, this should be it. So it should just be going at a constant velocity of 1 meters per second for all of 20 seconds. We should have plotted velocity, but that's what it is. We can look at that's pretty much it, I think. The next thing that we're going to go into is when there's an unknown, when your model is not perfectly known. So in this case, I'm going to use a damped model of the cart, where I put up a damping ratio of 0.005. If you know what damping is, it's basically just friction while you're moving on the road, which is expected. And a lot of the times in real problems, we don't end up knowing the damping coefficient to a lot of accuracy. So we're going to be using that problem as an example instead of using disturbances. So I set a damping ratio of this value, and mind you, we don't know that in our control. So I have an A real and a B real, and let's see how our control sequence does given our U control, and then there's the real damping in the word. So this is open loop with damping. I'm going to change that into with damping. So this is real world. And this is what it looks like. I forgot to add tires to that thing, but you can imagine, right? So it will not make it to 15, which is expected because there's damping in the world. I think I changed my goal here. Yeah, our U control changed, but that's what would have happened if that was the case. Let me just get the U control back for the final code, but I'll leave it back in. So the thing to note here is that you don't know the A real and B real. You don't know the real model of the world. You're only given the other model, and you're asked to get all of this. So you go, you measure the distance, and you go, this is how much I want to be accelerating if I want to reach at a point that is 15 meters away in 20 seconds, and this is going to be my control. But then you apply that control in real world, and it turns out that the world wasn't as nice as you expected, which will happen a lot of the time. So I'll run this. But then from our project, we know that the idea in there is to use an MPC controller or any feedback control to be real. So in a feedback control, what you do is you find one control sequence. So from computing, this is basically our horizon, right? We say we're going to plan, I'm going to look, say, 20 steps in front of me. I'm going to look in the future where I'm expecting to be in 20 seconds, 20 time steps, which is like 2 seconds for us. And then, depends on your control horizon, it can be anything. Let's say I choose it to be 20, so 2 seconds. I'm going to look 2 seconds in the future, and I'm going to try to get to my goal in those 2 seconds. And this should be my control sequence for those 2 seconds. Then I take the first control, I get the full sequence of controls. I know everything that I'm going to do for the whole 2 seconds, but instead of doing everything for the 2 seconds, what I do is I just find out by that logic, what am I doing at this instant? So I just get the first control. So at this instant, I'm doing this. Then in our simulation, what we end up doing is that we propagate that model. So I get my control from my cart MPC function, and I propagate it using this A real and B real. To be fair, this is different from the problem that we have in our project, so this might not be You can't just copy paste it. It's a different problem. But the idea is the same. My prediction then from the real world, because I just calculated my control, I put it in a car, and that's how much I'm gonna put throttle in my car, and I find out where I am at the next time instant from the real world. Then I again look at, I'm at this new position, then I say, okay, I want it to be somewhere else, but this is where I am now. I'm gonna again look 2 seconds in the front and say I'm gonna reach my goal. So if I have to reach my goal in the next 2 seconds, what should be my next control? I keep doing that, and I keep doing that, but you have to note that at each time instant, I'm measuring where I am, then I'm planning for a particular time horizon, then I execute my control for that time instant, and then at the next discrete time instant, I again note where I am and then replan, and then again execute and then replan, and then execute and then replan. So whatever was the error that you accumulated because your model was not perfect, your model didn't take care of the dynamics, your MPC should be able to compensate for that. So when you were doing it with the damping in real world, you stopped somewhere around 10 meters. The MPC should be able to take care of that. I kind of went back a little bit also. So I run this. Let's run this. And then I just call it like that. And the MPC should be able to reach the goal even when I'm still simulating. So with the SIM card MPC, my trajectory is in the real world. It's simulating with the A real and B real instead of the other cart models. So this trajectory is in the more difficult world, the real world simulation. So this should be MPC battling imperfections in real world. Open loop in real world. That is the world with damping. So it looks, I changed the legends a little bit, but that's what it is. And you will see that MPC, which is the red card, it should still be able to get to the goal, and it does. And the other one, the blue one, which is the open loop control, which doesn't take care of the damping, which doesn't remeasure and reconfigure, which doesn't learn from its mistakes, its errors, it has a problem. I also put in a pendulum example. This first part of the problem is in the Appendix C of our book. The modeling is probably not required for you, but if you're taking a physics course, you might be interested in seeing how this equation came about, because it's literally just drawing a free body diagram and just balancing your forces. So this could be interesting to you. And then we solve it using Euler integration because the model is nonlinear. We can't have this prediction of xk equals xk plus 1 equals a times xk plus b of uk. We can't do that. What we end up doing is we look at x dot equals ax plus bu. So we have a model that is x dot equals some f of x, and then from there we get x dot equals f of x. We do symmetric differentiation, and then our equation is of the form xk plus 1 equals x at xk plus 1 equals x at k minus 1 times 2 times delta t, I missed a 2 in there, times f of xk. Let me fix that. Let me put the 2 in there. Yeah. by that logic, I define a pendulum in the real world. And I also end up, this is not a part of the book, but if you want to look at where I found this pendulum, where you apply a force to the pendulum, you can refer to this article right here. But basically, this term changes right here, and it's given a control sequence U, which is basically the force that you're applying and for how much time you're applying the force. So I set up a problem here, a forced pendulum. It takes the initial position, the simulation time, the time for which you're planning or simulating, and then a control sequence U. I'm going to use this function to wrap the position. So my state in this case is the angle theta of my pendulum, and this isn't an inverted pendulum. It's like a normal pendulum, like simple pendulum. And the states are basically theta and the rate of change of theta, which we call omega in physics a lot. So I'm just wrapping, I'm keeping everything within minus pi to pi. So if it's like going around, if it's more than pi, I'll just bring it within the interval of minus pi to pi, because it means the same thing, right? So that's that function. And then, let's see. So let's do an unforced case. So I do pi by 4. And I'm going to make this unforced. Basically, it's a forced pendulum. I call the function forced pendulum, but I'm giving it no force. So it's like an unforced system. And in discrete time instances, this is what it looks like. This is my angle theta. And then this one is in continuous time, which is, again, my angle theta. And then I also made an animation for our pendulum. So I started at x equals, my initial angle was pi by 4. So my pendulum started from 45 degrees in the air. And because we're working in a frictionless world, it will keep going on and on and on at making pi by 4 degrees, as you can also tell from this plot of the angle with respect to time. Your problem is, I'm not going to solve this here, but your problem is you're trying to find a control sequence, a minimum norm control sequence that can force this pendulum to go in a circle. So I'm going to start it from this rest position. If I give it no force, as you will expect, the pendulum just stays at rest. So it just stays at rest. There's no force. It'll stay at rest. But if I gave it a force of, let's say, 2 meters per second, 2 newtons, I don't know what the, what is the Newton meter? Force. Force is newtons, right? Yeah. So if I gave it a force of 2 newtons for the first this isn't even like 1 second, 1.1 seconds, this is what happens. It oscillates, and it's kind of jerky, but it oscillates, and it doesn't fully go out. It goes to some 0.1 value. It looks like that. It's a very small perturbation. Let's say I give it that perturbation for a longer while. Let's see what this one looks like. It's going to go to 1. It's still not like pi by 2, so it's going to be a lot more of the perturbation. Let's say I make it, I'm going to make it 5. And yeah, this one will throw it off. As you can see, it goes like between minus pi to pi, which just means it's going in a circle. This is what you want, but this is not, again, this is a manual input. This is not the minimum norm solution. This is, again, an underdetermined system of equation that you're going to want to try to control, and you're going to try to find a minimum norm solution to this. But basically, this is what you want. You want your pendulum to go in a circle. And you want to do it with the minimum amount of force, because that's what we're after. And we know how to do that, but this is a practice problem for you. You have a nice simulation. You can play around with it. And I was going to go into the details of it, but in the interest of time and also just in general, nobody's here. I don't feel like going into it, but if you're interested in the problem, post on Piazza, and we can take it up from there.